itself was expected. Okay, so nice to see you all again. Bonus question on yesterday's discussion topics that came up twice in my talk and in Francie's second talk. Axe-Grothendieck, bonus level, it was proved that the an injective polynomial map Cn to Cn has a polynomial inverse. I think, but this part I didn't found an answer to this part. Is there a model theoretic take on that part? So this part of the argument, I know a non-model theory proof. I never thought about it too hard, but I never saw a model theoretic proof. Well, maybe other people know that. Okay. And another kind of thrust from yesterday's talk was an exercise I just wanted to pose to you. Another exercise of the form, go and look something up, which is if you've never come across the hyperreal numbers, then now would be a good time to look that up. And the hyperreal numbers might be some sufficiently large, or arguably some particular elementary extension of the real numbers as maybe in a language of rings, maybe in a much expanded language where we've thrown in all the function symbols and all the relation symbols that we would ever care to think about. So if you do that, that's the game I was telling you about yesterday, where you can add things to structures and still take elementary extensions. Perhaps ultra powers will be one very concrete way of doing that. Then in such objects one can do what's called non-standard analysis, which provides another kind of framework for many things, but for example basic calculus. So that's kind of something fun to look at on the topic of yesterday's. All right. So today I say something more about value fields. So most of us have seen what a value field is before, but let me go right from the basics definition. A valuation on a field K is a function v from K to some gamma. Gamma will be an ordered abelian group. This means a totally ordered abelian group, which I will always write additively. That's, of course, a choice of convention, such that, well, it flips the convention of normal size measurements in mathematics, right? Instead of saying that 0 ought to go to 0, we say that 0 ought to go to something infinite, namely a symbolic infinity. And that's the only thing going to infinite. It's kind of upside down from the usual conventions. We want it to be some kind of morphism, specifically multiplication goes to the addition. And if you think of absolute values, you have the triangle inequality here. So instead of that, we're going to have what's called the ultrametric triangle inequality, which somehow bounds how big a sum can be. But since we're doing something upside down, it's greater than or equal to the minimum. Now that's not only different in the sign, it's different in that we've got this minimum, which if we were thinking about the world of absolute values, that would be like saying that the absolute value of a sum is no greater than the maximum of the two absolute values. Well, that's still different to the usual triangle inequality, and that's exactly what the word ultrametric means. And I mean, I think one casual way of saying it is that in ultrametric geometry, every triangle is isosceles. And a usual kind of corollary of this, one can deduce, quite quickly that if you have two numbers, x and y, in such a valued field, and one is absolutely smaller value than the other, then the value of the sum is actually equal to the minimum. That's just a slightly unusual property. Exercise deduced that in a couple of lines from the axioms. Well, I'd better give you an example straight away. Oh, by the way, I missed something out. I like to have the convention here that this should be a surjective map. So that tells us that this particular group here is somehow, is the right group. That group is known by the function. And I'll give you an example, but just first let me call that the value group. And sometimes that's denoted something like VK, like that. Okay, example. The first and the best is you take P, a prime number, consider the p-adic valuation on Q defined with value group Z added to the ordered abelian group, and it should do the following. It should take any rational number, which can be written, of course, given our fixed prime P, as some P, L, M, N, for integers L, M, and N. Now, they're not unique if you write any rational number like that, of course, but they're nearly unique if you insist that M and N are not divisible by P, then you've only got minus signs to worry about. So that doesn't matter for our purposes, and this we map to L, so it's measuring how many P's divide into a given rational number. And 0 goes to infinity, of course. Now, it's an easy exercise to check the axioms, but let's just do a silly example. Something like that. I imagine most people have seen this kind of thing before. Okay, so that gives us this family of p-adic valuations on Q, one for each prime. Let me now show you another valuation, example 2. Maybe I'm running out of space, so I'll tell you what, I'll take this opportunity to give some notation. I will call OV the set of x's with value greater than or equal to 0, which plays the role of the closed unit disk, kind of, in the analogy with an absolute value. It's a closed unit disk. That's a ring. That's a local ring. It has a unique maximal ideal, which coincides with the set of elements in the field that have strictly positive value. That's the maximal ideal, or the valuation ideal. I already said that gamma V, or gamma, sometimes called VK, something like that, is the value group. And whenever you have a ring and a maximal ideal, you can form a quotient, right? And so we call that the residue field, and sometimes that's denoted something like little kv or big kv, like that. And that's just the quotient. That's called the residue field. And of course, we have a map, the residue map, that goes, it's the quotient map. And so this map and the valuation itself, I tend to think of them both whenever I think of the valuation. I'm not really just thinking of the valuation, I'm thinking of all of this information. And it's a valid question, what's the right way to kind of code up a valuation into some first order language, into some formal structure? What's the right kind of data to bundle together? And that's a question that has several right answers. actually the simplest answer would probably be to think of a valuation kind of as a pair, just the field. I'm ignoring to write, I'm not writing down any of the field structure here. The valuation as a sort of distinguished function, so I'd better throw in somehow its codomain, or at least most of its codomain. And that's one way of beginning to think about valued fields like a first order structure. Before I get more into that, let me go back and give you the second example I promised you. But in case you're wondering how to think about all these little objects flying around, there's several choices, so it's natural to wonder. So the second example, take any rational function field like that and write the t-adic valuation, which just takes well, actually let me write it like this. So it would take a polynomial so any polynomial you can write down, and you can ignore indices that are too big, the coefficients are 0, or too small. So I could write maybe I goes from little n to big N, and in both kind of, there's always a most efficient way of doing this, except for the 0 polynomial. Let's not worry about that because we know that's going to go to infinity. So I could look at this n, the degree, but actually for our purposes today, I really want to focus on this little n, and that's the t-adic valuation, which is kind of taking a polynomial and asking a similar question about t, namely how much does t divide this polynomial, that we asked about p in Q, sort of thinking of the integers, right? We had ratios of integers, and I asked how much did p divide the numerator, how much did p divide the denominator, and here, if I have one polynomial, I ask how much t divides it, and if I had a ratio of polynomials, well then I just send it to the difference, right? Defined by this line. That sort of has to be the right definition to make, because I insist that multiplication goes to addition, so division better go to subtraction. And of course you should check some details here, check that these basic assumptions do hold. This is a valued field. Let's look at what these associated objects are in this case. Maybe I can make a little table. So in the p-adic one, this is Q as a p-adically valued field, and then I've got this kind of rational function field as a t-adically valued field. So what's OV in Q? Any answers from the audience? And I'm not addressing people that have seen this before. I'm not addressing people that are comfortable with this. So I want vulnerable guinea pigs. That's okay. So we know that we're asking which are those rational numbers that when you ask how much p divides me, it's non-negative. So certainly integers better be there, right? Because 1 over p isn't an integer, and anything with a bit of p in the denominator isn't an integer. Right, so it's got to be something like the integers. But if p is 3, then 1 over 2 is in there. And that's not an integer, so it's definitely bigger than that. Well, it is exactly the localization of z of p. Most of us have probably seen that. And what about here? Well, it's the same sort of game. Okay, same game. What about the maximal ideal? Well, we've seen this maybe. It's PZP, and that's T, KT localized at T, like that. What's gamma? Well, I already told you that's Z in both cases. And what's the residue field? Well, here, what are the classes mod P in this ring? Well, actually, Z already represents that. So Z, quotiented by P, already surjects onto ZP, quotiented by P. So we get the same result, which is FP. And here we get K. Just check that. So we've got two valued fields that, have something in common, right? They're both Z valued. They've both got principal maximal ideals. Yeah. They're both discrete, right? Okay. So we can take a completion of such things. Now the completion can be defined for an arbitrary gamma. I haven't given you any examples of big gammas yet, but I will in a second. But it can be defined for an arbitrary gamma, but I just want you for a moment to think of the completion only when the gamma value group is Z itself, or something like Z. Something contained within R, something you would call rank 1. So for the completion, it is true that if gamma lives within R, then we actually do have a metric here induced by any gamma valuation like that. So we can certainly take a completion as a metric space, and indeed, with a lot of not difficult checking, one can check that indeed takes a natural field structure, takes a natural valuation, and there is a universal property that you would expect, which is that any embedding of KV into a complete value field with the same value group, same residue field, will split, but will factor through this embedding. Yes?
How do we account for the infinity?
How do we account for the infinity?
Because we have gamma being... Oh no, sorry, it's gamma union infinity up there. Never mind.
Yeah, so that's supposed to be taken as just some extra symbol.
Okay, and that doesn't influence our metric at all? Because it's not part of gamma?
So maybe I brushed over that a little quickly. What's the metric? How do we actually put our fingers on the metric here? Well, e.g. in Q with VP, right? What is this? I'd rather define the absolute value, if I may, and then the metric is just, of course, the absolute value of x minus y. How do we do that? Well, pick your favorite number bigger than 1 here. I liked p. Then you stick minus vpx here. Right? Now, what have I done? Well, that doesn't quite make sense, does it? Because there's no such thing as p to the minus infinity. Well, I can say 0 when vp is infinity, which exactly is the x is 0 case. So that's more strictly how you do it. And this highlights, doesn't it, that we've got a choice here. We've got lots of choices to make. This is not any kind of canonical thing, is it? Because I picked some sort of normalization here. That was totally arbitrary. I picked the p because it looks nice. I could have picked a totally different number. So that would be some notion of equivalence, and there are similar notions of equivalence on valuations, which I'm just going to skim through now. So different notions of equivalence. Between valuations. Just a very quick skim. Take two valuations, v and u, on a given field k. They are equivalent if there's some isomorphism of ordered abelian groups between their value groups, such that this diagram would commute. Okay? So what's that saying? Two valuations are equivalent when it's just a matter of rewriting the the codomain. That's a very natural notion of equivalence, and you're quite right if you think, well, obviously any two valuations are equivalent. That's a boring difference. That's almost always a negligible difference. So we'll almost always think up to equivalence. And one can check that the map, the class map, if you like, that takes valuations to valuation rings has as its kernel exactly this equivalence relation. So this comes back to the question I was just getting at a moment ago, which is, what's the right way of thinking about valuations? And I said, well, there isn't one right way, which is my favorite kind of answer to any question. Well, this tells you, this measures exactly the difference between thinking of valuations or thinking of valuation rings. The difference is precisely this notion of equivalence. Nothing more, nothing less. And for most of our purposes, it'll be harmless to move backwards and forwards, but it's worth always bearing that in mind. Okay, next notion of equivalence. So that was level 1. Level 2 is not strictly a notion of equivalence, but U can be finer than V. And for me, finer, less. I guess I'm saying, or equal, finer or equal. And dually, one could say V is coarser or equal than U if the valuation ring is literally a subring of the other valuation ring. So this is saying what's the pullback onto the set of valuations on a given field of the natural inclusion subset relationship between valuation rings on a given field. And that's just this notion of finer and coarser, and that's a pre-order, and this notion of equivalence is exactly the we're both finer and coarser than each other notion, isn't it? So these are obviously these go together. Yeah.
You mentioned the kernel of that map. Is that kernel in like the category theoretic sense, or do we have like a zero, like an OV that functions as zero?
No, I meant it in the sort of, if you like, the category theoretical sense, but I'm in a way just being less formal than that. I just mean, what does it mean that two things get mapped to the same thing?
Okay.
Under that map. And it's only a map in the broad class sense, right? Excuse me. Now this is a big difference, right? If valuations are finer or coarser than each other, that's very useful to think about, and that will pop up again a bit later. And I needed to tell you that because there's this third thing I want to tell you, which is that U and V are dependent if and this is a definition, if they have a non-trivial I didn't actually say what non-trivial means, finest common coarsening. So now I need to just check my notes to make sure because I definitely left out one case. I wrote that they're independent, even only if their finest common coarsening is the trivial valuation, and at least one of them is non-trivial. Okay, so yeah. Well, let's just say that these are non-trivial. That's always a bit confusing to me. You don't really want to include the trivial ones. So, what does non-trivial mean? Anyway, that's the case when the valuation ring is already the whole field, or equivalently that the group is a trivial group. Okay. Or equivalently that the residue map is the identity map, or that the maximal ideal is just the set with 0 in it. That's a trivial valuation. Okay, now why am I telling you all of this? Because understanding the relationship between refinements and coarsenings on valuations will be quite important later on in this video. Let me just give you a few.
Sylvie?
Yep.
The definition of dependent does not a priori contain the word finest, right? You have to show it that there is a finest one.
Well, I mean, I think the definition works, right?
Well, after you show that if there is a non-trivial common cause, I mean, there's also the finest one.
Well, I mean, I think that's showing that things we want to be dependent are dependent. I mean, I think this is a valid definition as it stands.
Is that equivalent to saying that they're independent if their intersections of the valuation ring is like trivial or something? Or
No, it's a bit different to that. Yeah, it's different to that. That'll never be quite the case. I agree with your point, Hans Victor, that to check that valuations have finest common coarsenings when you want them to have a finest one is a subtle point. But I guess that's a matter of showing that certain things that we sort of know are dependent are in fact dependent. Okay. So fun exercise now. Investigate. I won't because I don't have time to tell you everything, of course. Exercise. Think about the topology coming from evaluation. And it's a topology with well, let's say a priori a subbasis given by sets like this of balls, which are all the elements in the field whose value, when you take away the sum center of a ball, is greater than some gamma, and here we range over all x's in K and all gammas in gamma. Now, as it happens, the intersection of two balls is in an ultrametric setting is either empty or itself a ball. So that means this is actually a basis rather than a subbasis. But never mind. All right. So just think about that, and there's a reference in the online notes for a nice paper about that. Yeah.
So this is really like the complement of a ball in the geometric sense, it's greater than gamma?
Well, no, because the intuition is flipped upside down. So evaluation is just in the way I've written it. One could write everything the other way up, but then other parts of the story become a little less cute, I think. So you want to think of that as just being the analog of writing, that time. All right. Now, I wrote another exercise. That's an exercise just to look up the reference, and I say check that or investigate that the sets A times U, where A goes through all non-zero elements of Q, is a basis. Well, that's a claim, I guess. Investigate this family, hint it's a basis or something, where well, and actually I mean this also. Let's say AU plus B, and that's for A in Q times and B just anything. And that's where U is a set like this, 1 over 1 plus x1 squared, x2 squared, x3 squared, x4 squared, blah, 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 minus, same thing with some y's, 1 plus some yi squared. There should be 4. Let's write it like that. Sum x I squared is this 4. Okay? And these better be rational numbers. Okay. It's just cute to play with. Have a little play with that. Okay. Next slide. So what I want to do in the first lecture, which has another half hour in it, I want to state the Kochen and Ershov theorem in equal characteristic 0 and prove a baby case of it. And then I will prove it in the second lecture. So the Kochen and Ershov theorems, which are the kind of theme of my talks, are theorems that tell us how to calculate or how to find or how to describe the first order theories in a suitable language of various valued fields subject to suitable completeness type hypotheses. Now, equal characteristic 0, haven't said what that means exactly yet, is a nice setting where things go well, and things go so well that, from the point of view of answering that basic question, what are the complete theories, I would say we have a pretty perfect understanding. The difficulties, from my point of view, come in positive residue characteristic, and that's what I want to spend time focusing on later in the week. But for now, let me introduce the completeness type hypothesis that plays the role of our sort of background setting in which all of these theorems will hold, and that's henselianity. Okay, so henselianity. A valued field a V is henselian if for all monic f polynomials over the valuation ring in one variable and all elements A of the valuation ring, if the value of f at A is positive and the value of the formal derivative of f at A is 0, then. Before I say the then, before I say the conclusion, what's this about? What are these two assumptions about? Well, let's draw a little picture. Right, we have this valuation ring, we have this quotient map, which takes us to the residue field. Every polynomial here has an image over here, right? Every element here has an image over here, and I can evaluate this polynomial at this element, and of course that's the image of this polynomial at this element. Boring. Now, it might be that a polynomial f has a 0 at A, in which case this will also be a 0. It might be that this is 0, but this isn't. And henselianity is exactly a hypothesis that tells you when that 0 lifts. Right? That's what it is. It's a tool that tells you when the 0 lifts. But of course, not every 0 lifts, even in the nicest of settings. So there are some hypotheses. Let's just check what those hypotheses tell us. The value of the polynomial at this given point at which we play is positive, which means the hypothesis there says that f of A goes into the maximal ideal, which means goes to 0. So this hypothesis exactly says that we do residually have a 0. Okay? So what does this hypothesis say? Well, this hypothesis says that f prime of A does not go to 0. Right? Which is like saying you've got a simple root of a polynomial. So in the residue field, you've got a simple root, and the conclusion is there exists, and in fact it's a unique, as long as I say such that, a unique B in the coset of A, or near to A, such that f of B is 0. Yes?
What's the valuation on OV in one on polynomials in OV in one variable?
I'm only actually writing V of something when that something is an element, right?
Oh, you plugged in A.
I plugged in A.
I didn't realize that. Okay.
But you can. There are many ways of, in general, of extending valuations to polynomial rings and other such things.
Okay.
Okay. So that's the definition. Now I said it's a completeness-like property, and that comes from the fact that it's, in some sense, strictly more general than completeness. But we need to be just a little bit careful when we say that. So the lemma, which I won't prove in its gory details, but I'll just say one word about, which arguably is called Hensel's lemma, which is that a complete z-valued field, so when the gamma is z, can't spell today, sorry. Complete z-valued fields are Henselian. Must have been amazing to work on a statement about Henselianity when you're called Hensel. What are the chances? Wonderful. Lucky devil. Okay, so what is it? Well, that's an approximation statement, isn't it? I mean, anything you're proving that works in a complete object, and that's an important hypothesis, is going to be because you can approximate the roots using the tool, using what am I trying to say now? Subject to these hypotheses, you can improve a root, and then completeness tells you there's a limit there. Yes.
Is it important that your value group is discrete? It seems like Archimedean is kind of how you build your Kochen sequence. What if I like Q as a value group or something like that? Can you still get
Actually, rank 1 valued field.
rank 1?
Rank one for this statement is good enough.
Okay.
All right. Now I'm not going to, as I said, I'm not going to prove that, and there's references in my online notes. What's important for us is that just like a completion is the sort of unique, is the closure of a something under the property of completeness, there is a Henselian closure, which I now want to just name for you. Definition. The Henselization of KV is a valued field, is a VF, KH, VH, but I really want you to think of this as it's an extension of valued fields, satisfying the obvious universal property. Namely, if you've got a given embedding of KV into LW, and LW happens to be Henselian, that should be an embedding as valued fields. I haven't actually told you what that is. You can go and look that up. Then it should factor through this. And uniquely. And indeed, this then turns out to be unique up to valuation theoretical isomorphism over K. Now, it's a fact, not an easy fact, that Henselizations exist. that's easiest seen through ramification theory, looking at the absolute algorithm. Okay, so there's a bunch of exercises that I've got for you in these notes, but I think for the sake of time, I'm just going to keep moving on. I want to tell you another key ingredient now in this sort of background theory of valuations. The fundamental equality, sometimes called fundamental inequality, just temporarily step away from the Henselian world. I want to say now for a valued field kv and a finite field extension L over K, we have the following equation, which is that the degree of this field extension is exactly a bunch of things. It's a sum over the finitely many W valuations on L that extend V, which I'll write maybe just like that. Or I could write, it's the W's and I implicitly mean on L, such that when you restrict them to K, you get V. Now, I want to write now 3 numbers in here. The first is E, which is going to be, I'm going to write E of W over V, but let me at the same time tell you what that is. That's the index of the value group of V inside the larger value group of W. The ramification, right? We've all seen some algebraic number theory, and that's exactly what's going on in like factorization and embedding things. F, same as in basic algebraic number theory. This is now the degree of the residue field extension. And then it's multiplied by P. I haven't told you what P is yet, so just hold that thought. Times some D. So I need to tell you what P is and what D is. So P is 1 if the residue characteristic, so if the characteristic of KV is 0, or it's P if the residue of KV is P. So it's the characteristic exponent of the residue field. And this is called the defect. Sometimes this whole thing is called the defect. As you like. Doesn't matter. And that's just some natural number. Now the good news is, if you believe this equality, then you already believe that everything's nice in characteristic 0. Because in residue characteristic 0, in a residue characteristic 0, this is saying that whenever you have to extend a valuation to a finite field extension, it's good enough to, or we're given intuitively it says each valuation that you want to look at is exactly somehow fully described, go along with me, by its ramification degree and its inertia degree. Intuitively, that maybe is what this is saying, and that's kind of the philosophy that we'll use in the Kochen Ershov theorem as well. But we already see in this equality that something much nastier is happening in residue characteristic P. Yes?
So does this mean there's given a finite field extension L over K, there's always, does it bound the minimum number of?
Well, that's a great question. And if this has, arguably, yeah. I'm just so certainly there is a minimum number, which is 1.
Mm-hmm.
Indeed, sometimes there is only 1, and that will be something you can also sort of read off this data, right? Because I mean, though maybe that doesn't quite make sense, because what would it mean if there weren't anything? But look, an empty sum should be 0, and if you extension ought to have degree at least 1, I think. But I think, you know, so I'm saying yes, that sort of fits. That fits. All right, now, again, don't have the time to prove that here. What's the idea, and where do you find the real proof? Well, the idea is, well, actually, I'll answer that question backwards. The real proof, you want to look in, I think there's nowhere better to look than the valuation theory book by Enger and Prestel, which is in the online, which is referenced in the online version of this talk on the notes. And what's the idea? Well, the idea is first prove it for normal extensions. Because in a normal extension, or normal field extension, all the prolongations, all the extensions of the valuation are conjugate. That doesn't make things trivial, but that's certainly the first step. Another tool is that when you lift linearly independent things happening in residue extensions, and when you lift additively independent things in value group extensions, and you take a product, just like you would do in a Tower lemma argument, you get something independent. So that's the way of building linear independence over capital K from things coming somehow independent in the value group and residue extensions. So that's the intuition. And that trick, by the way, that sort of Tower lemma business of taking products of lifts of independent things plays many, many roles in this subject. Not just for calculating degrees, but for actually finding sort of bases of things as well. Okay. So that's all I'm going to say about the idea of the proof. But let me give you a kind of couple of consequences right away. Corollary, defect, trivial in residue characteristic, i.e. the characteristic of the residue field, 0. And separate statement, but that falls from the methods or falls from related methods. Defect is trivial for Z valued fields. And I didn't say it explicitly, but when you have an integral domain O, the residue field little k, of course, if O has characteristic 0, then in principle you can have k's of residue characteristic any p or 0. If OV itself has characteristic p, you can only have p in the residue. That's pretty clear from just...
Not in positive characteristic.
Sorry?
Not in positive characteristic. Schmidt example.
Sorry, what you're just talking about the thing I'm just saying?
Positive characteristic.
Yeah.
You have subfields in FPT, algebraic T, which constitute a defect extension.
Yeah, I'm sorry, I mean to say here for Z-valued fields of characteristic 0, so when capital Q is 0. Yeah. But the point is that's not strictly a corollary, but it follows from the same family of methods, yeah.
What does it mean for defect to be trivial?
Well, it means that the D here you can I mean I'm saying that we can ignore this factor.
Okay.
And if P is itself positive, is a prime number, then trivial defect would just mean that it's 0.
Okay.
According to this convention of writing it.
So it means trivial defect means that last term, whatever it is just 1?
The last multiplicative term is 1.
Yes.
The exponent could be 0.
Yeah, it could be 0 or it could be base 1.
Exactly.
Okay.
It's just a convention. Do you write it as the exponent or as the whole thing? That's it. Okay. So now I want to come back to that question that I mentioned much earlier. What's the right way of thinking about valuations for our purposes? So this is the question, what's the right language? So for a model theoretic study, we need to choose the language, but that choice should be a realistic one. It shouldn't just be something that doesn't reflect the complexity of the objects involved, right? So this is a sort of choice, this part. What's the right language? Well, certainly we've got to be working somehow over the language of rings that I talked about yesterday and that Francie talked about yesterday. So one choice could be we just take the language of rings and we add a unary predicate symbol for the valuation ring. So this would be a unary predicate symbol. Essentially it codes up X is in O, right? And then in your quantifier-free formulas, you would just allow extra sort of conjunctions, disjunctions, negations, implications, etc. of statements like a term is in O. A term in however many variables is in O. That's one choice. That's a perfectly good choice. I already hinted at second choice. We could just we could write something like this. We could think about this sort of object. What is this? This seems to be a triple of a field, an ordered abelian group, and a function connecting them. You can code this up in a sort of in the usual logic. We could take the language of rings. We could take two predicate symbols. We could take also the language of groups. We could insist that on the first predicate we have a field and that the interpretations of the symbols go as we want them to. And on the second, we have and that the two things are disjoint. We could sort of squeeze rather artificially two languages into one. We could have the sort of the ring in one part of the structure, the field, and we could have the ordered abelian group in the other part of the structure, and so on. We could do that. I personally find that a little bit ugly. There's a much better way of doing it, which is just to redo all of logic, where you allow two different kinds of variables, and just keep track of everything very carefully with different sort of sorts for each variable. And so, rather than this sort of horrible artificial way, we just allow two sorted logic. We have one sort in which we have the language of rings, we have another sort of variable which we have a suitable language of ordered abelian groups, and we have an extra function symbol going between them. And then formulas, you need to now be a bit careful that you only use the right variables for the right terms and so on, but that's okay. So two sorted logic. That's one other choice we could make. Okay. A third choice we could do a three-sorted version. This is the version I like best because it sort of includes all of our favourite objects in one go. So this would be a three-sorted version where we, in the logic, in the underpinning logic, we allow one sort of variable that we label with a capital K. And that gets the language of rings. We get another sort of variable that gets a suitable language of ordered abelian groups. And we get a third sort of symbol that also gets the language of rings. And in an actual valued field, of course, we throw in, when we want to interpret an actual valued field as a structure of this kind, we of course put the main field itself here. We put the ordered abelian group here, the value group. We put the residue field here. We put the valuation map here, and we put the residue map here. These are then two function symbols connecting slightly different sorts. The V goes from the sort K to gamma and the res from big K to little k. One needs to be a little bit careful because, of course, we don't want that the residue map is defined on all of the field, because really you're only quotienting the valuation ring, not the whole field, so you need to have a convention to get over that. But for me, this is the language I would like to think of as our language of valued fields. If that looks a bit horrendous, which I think it did to me for a long time, then just think about this one, where essentially you've just got an extra way of picking out I'm in the valuation ring. So this is the language I'd like us to think about valued fields in. And yeah, okay, so formally speaking, how do we sort of construe any field with a valuation as an L-val structure? Well, we think of it as a sort of 5-tuple, where the first element in our 5-tuple is technically the field as an L-ring structure. So that's a sort of tuple of things, isn't it? Like that, blah, blah, blah. So on, the second thing will then be the value group and so on. But that's going to have a plus, it's going to have subtraction, it's going to have a 0. It's probably got a separate symbol for infinity that I haven't discussed with you in detail, and so on, right? So technically, that's how you construe a valued field as an L-val structure. And as I say, if I can call this one, can I call this L-val superscript 1? Because it's the one sorted version. There's no extra funny multi-sorted nonsense going on here. Okay. And this is just L-val. And L-val and L-val1 are, for most purposes, most but not all, are for most purposes equivalent. That's a bold statement maybe, but certainly for this week I'm not going to say too many things that depend on one or the other.
What would depend on choosing the different version?
Complexity of formulas. Because to write a formula somehow that where you can explicitly refer to all of these extra things, but somehow only allowing yourself to talk about this predicate often means an extra bit of quantification. There's a bit of loading of the concepts. In logic and model theory, that's called interpretation. So any valued field as an L-val1 structure is in fact bi-interpretable with a L-val structure of the same object. Bi-interpretable is, again, it's a slightly subtle notion, but essentially it means that they see each other and you can code one in the other. It means a little bit more than that, but you often get a complexity cost.
Yeah.
There's a cost of transaction.
Excuse me? For example, for QP, for p-adics, in which language you will have elimination of imaginaries?
I'm not going to get as far as talking about that in this course.
I'm just asking the result.
Elimination of imaginaries in the p-adics, I don't know off the top of my head. Maybe someone else knows.
Observe.
Yeah, not in any of the languages so far.
Oh, okay.
But we certainly, yeah. I mean, there's lots of things we don't get in these languages. Okay, so let me now state. Let me just state an observation. There is an L-val theory there are L-val theories of valued fields and of Henselian valued fields. So I can write down axioms that say, I am a structure of this kind coming from a valued field. I am a structure of this kind coming from a Henselian valued field. And your exercise, I've given you many exercises, is to prove that this one, this is quite a hard exercise actually, is not finitely axiomatizable. Okay, and in the final 2 minutes, I get to at least state something which I hope to prove, which is, I'll give you one more definition. ACVF is the L-val theory of algebraically closed fields with non-trivial valuation. And then ACVF, sort of, 0, 0, or 0p, or pp, take their obvious meaning. Extra axioms to force the characteristic or the residue characteristic. And the theorem, which is actually quite easy to prove, is Abraham Robinson, is that, can I call one of these things, can I call that sort of L comma Q or something like that? Just one of these choices of 0, 0, 0p or pp. ACF LQ is complete in the sense that Franzi introduced, and all completions of ACVF are of this form. It's a classification of the completions of ACVF. And that's quite easy to prove, and I'll prove that in the first few minutes next time. Later today.